Resource acquisition is initialization is a programming idiom used in several object-oriented languages, most prominently C++, where it originated, but also D, Ada, Vala, and Rust. The technique was developed for exception-safe resource management in C++ during 1984-89, primarily by Bjarne Stroustrup and Andrew Koenig, and the term itself was coined by Stroustrup. RAII is generally pronounced as an initialism, sometimes pronounced as R-A-I-I. In a RAII, holding a resource is tied to object lifetime. Resource allocation is done during object creation, by the constructor, while resource deallocation is done during object destruction, by the destructor. If objects are destructed properly, resource leaks do not occur. Other names for this idiom include constructor acquires, destructor releases, and one particular style of use is called scope-based resource management. This latter term is for the special case of automatic variables. RAII ties resources to object lifetime, which may not coincide with entry and exit of a scope. However, using RAII for automatic variables is the most common use case. C++11 example. The following C++11 example demonstrates usage of RAII for file access and mutex locking. This code is exception-safe because C++ guarantees that all stack objects are destroyed at the end of the enclosing scope, known as stack unwinding. The destructors of both the lock and file objects are therefore guaranteed to be called when returning from the function, whether an exception has been thrown or not. Local variables allow easy management of multiple resources within a single function. They are destroyed in the reverse order of their construction, and an object is destroyed only if fully constructed, that is, if no exception propagates from its constructor. Using RAII greatly simplifies resource management, reduces overall code size, and helps ensure program correctness. RAII is therefore highly recommended in C++, and most of the C++ standard library follows the idiom. Benefits. The advantages of RAII as a resource management technique are that it provides encapsulation, exception safety, and locality. Encapsulation is provided because resource management logic is defined once in a class, not at each call site. Exception safety is provided for stack resources by tying holding the resource to the lifetime of a stack variable. If an exception is thrown, and proper exception handling is in place, the only code that will be executed when exiting the current scope are the destructors of objects declared in that scope. Finally, locality of definition is provided by writing the constructor and destructor definitions next to each other in the class definition. Resource management therefore needs to be tied to the lifespan of suitable objects in order to gain automatic allocation and reclamation. Resources are acquired during initialization, when there is no chance of them being used before they are available, and released with the destruction of the same objects, which is guaranteed to take place even in case of errors. Comparing RAII with the finally construct used in Java, Stroustrup wrote that in realistic systems, there are far more resource acquisitions than kinds of resources. So the resource acquisition is initialization technique leads to less code than use of a finally construct. Typical uses. The RAII design is often used for controlling mutex locks in multi-threaded applications. In that use, the object releases the lock when destroyed. Without RAII in this scenario, the potential for deadlock would be high and the logic to lock the mutex would be far from the logic to unlock it. With RAII, the code that locks the mutex essentially includes the logic that the lock will be released when execution leaves the scope of the RAII object. Another typical example is interacting with files. We could have an object that represents a file that is open for writing, wherein the file is opened in the constructor and closed when execution leaves the object's scope. In both cases, RAII ensures only that the resource in question is released appropriately. Care must still be taken to maintain exception safety. If the code modifying the data structure or file is not exception safe, the mutex could be unlocked or the file closed with a data structure or file corrupted. Ownership of dynamically allocated objects can also be controlled with RAII, such that the object is released when the RAII object is destroyed. For this purpose, the C++11 standard library defines the smart pointer class as std unique PTR for single-owned objects and std shared PTR for objects with shared ownership. Similar classes are also available through std auto PTR in C++98, and boost shared PTR in the boost libraries. GCC cleanup extension for C. The GNU compiler collection implements a non-standard extension to the C language to support RAII, the cleanup variable attribute. The following macro allows to annotate a variable with a given destructor function that it will call when the variable goes out of scope. This macro can then be used as follows. In this example, the compiler arranges for the fclsep function to be called before example usage returns. Limitations: RAII only works for resources acquired and released by stack-allocated objects. Heap-allocated objects which themselves acquire and release resources are encountered. However, even in languages like C++, and stack-allocated objects are unavailable in some languages, most notably in Java. For RAII to be possible for a heap-based object, in contemporary languages the programmer must implicitly or explicitly delete the object along all possible execution paths, in order to trigger its resource-releasing destructor. There are a number of possible workarounds and proposed extensions of RAII to heap-allocated objects. Reference counting: Perl, Python, and PHP manage object lifetime by reference counting, which makes it possible to use RAII. Objects that are no longer referenced are immediately destructed or finalized and released, so a destructor or finalizer can release the resource at that time. However, it is not always idiomatic in such languages, and is specifically discouraged in Python. However, object lifetimes are not necessarily bound to any scope, and objects may be destroyed non-deterministically or not at all. This makes it possible to accidentally leak resources that should have been released at the end of some scope. Objects stored in a static variable may not be finalized when the program terminates, so their resources are not released. Python makes no guarantee of finalizing such objects, for instance. Further, objects with circular references will not be collected by a simple reference counter, and will live indeterminately long. Even if collected, destruction time and destruction order will be non-deterministic. In Python there is a cycle detector which detects cycles and finalizes the objects in the cycle, though prior to Python 3.4, cycles are not collected if any object in the cycle has a finalizer. Also, in the case of Python, the garbage collection strategy is an implementation detail, so running with an alternative interpreter could result in the RAII implementation not working. Notes. References. External links: Sample Chapter Gotcha Number 67, Failure to Employ Resource Acquisition Is Initialization by Stephen Dewhurst, Interview: A Conversation with Bjarne Stroustrup by Bill Vinners, Article: The Law of the Big Two by Bjorn Carlson and Matthew Wilson, Article: Implementing the Resource Acquisition Is Initialization idiom by Danny Karlov, Article: RAII, Dynamic Objects and Factories in C++ by Roland Piebinger, RAII and Delphi one-liner RAII and Delphi by Barry Kelly.